An eigenvalue is a special number usually written as lambda that tells you how a linear transformation stretches or shrinks vectors that point in certain directions. Think of a rubber sheet with a grid drawn on it. When you pull the sheet, some lines may keep pointing the same way while only getting longer or shorter. Those unchanged directions are eigenvectors, and the factor by which they change length is the eigenvalue. The characteristic equation is the algebraic way to find those lambda values. For any square matrix A, we look at the matrix A minus lambda I, where I is the identity matrix of the same size. The determinant of this new matrix, det of A minus lambda I, is a polynomial in lambda. Setting that determinant equal to 0, det of A minus lambda I equals 0 gives the characteristic equation. Solving it yields all eigenvalues. Simple 2 by 2 example. Let A equals matrix with first row 3, 1 and second row 0, 2. Then A minus lambda I equals matrix with first row 3 minus lambda, 1 and second row 0, 2 minus lambda. Its determinant is open parenthesis 3 minus lambda close parenthesis, open parenthesis 2 minus lambda close parenthesis, minus 0 times 1 equals open parenthesis 3 minus lambda close parenthesis, open parenthesis 2 minus lambda close parenthesis. Setting this equal to 0 gives open parenthesis 3 minus lambda close parenthesis, open parenthesis 2 minus lambda close parenthesis equals 0. So lambda equals 3 or lambda equals 2. These are the eigenvalues of A. To form the characteristic polynomial, follow 3 steps. First, subtract lambda times the identity matrix from A. Second, compute the determinant of the resulting matrix. Third, write the determinant as a polynomial in lambda. Worked example, A equals a 2 by 2 matrix with entries 4 minus 2, 1, 1. Step 1, A minus lambda I equals a matrix with entries 4 minus lambda minus 2, 1, 1 minus lambda. Step 2, the determinant of A minus lambda I equals 4 minus lambda times 1 minus lambda plus 2. Expand, 4 minus lambda times 1 minus lambda equals 4 minus 4 lambda minus lambda plus lambda squared, which is lambda squared minus 5 lambda plus 4. Adding 2 gives lambda squared minus 5 lambda plus 6. Step 3, the characteristic polynomial is p of lambda equals lambda squared minus 5 lambda plus 6. Setting p of lambda equal to 0, we factor as lambda minus 2 times lambda minus 3 equals 0. So the eigenvalues are lambda equals 2 and lambda equals 3. This example shows the whole process in a compact 2 by 2 case. For a 3 by 3 matrix, the determinant expansion uses cofactor expansion, also called Laplace expansion. The characteristic polynomial is still determinant of a minus lambda I, but the algebra is a bit longer. Example matrix B equals a matrix with rows 2, 1, 0, negative 1, 3, 1, 0, 2, 4. Step 1, B minus lambda I equals a matrix with rows 2 minus lambda 1, 0, negative 1, 3 minus lambda 1, 0, 2, 4 minus lambda. Step 2, expand the determinant along the first row. Any row or column works. The determinant equals 2 minus lambda times the determinant of the submatrix with rows 3 minus lambda, 1 and 2, 4 minus lambda minus 1 times the determinant of the submatrix with rows negative 1, 1 and 0, 4 minus lambda plus 0 times, which simplifies to 2 minus lambda times the quantity 3 minus lambda times 4 minus lambda minus 2 times 1 minus 1 times the quantity negative 1 times 4 minus lambda minus 0 times 1. Now compute each parts. 3 minus lambda times 4 minus lambda equals 12 minus 7 lambda plus lambda squared. Subtract 2 gives 10 minus 7 lambda plus lambda squared. So the first term is 2 minus lambda times lambda squared minus 7 lambda plus 10. The second term simplifies to 4 minus lambda. Multiplying out the first term gives negative lambda cubed plus 9, lambda squared minus 24 lambda plus 20. Adding the second term gives negative lambda cubed plus 9, lambda squared minus 25 lambda plus 24. Thus the characteristic polynomial p of lambda equals negative lambda cubed plus 9, lambda squared minus 25 lambda plus 24. Multiplying by negative 1 optionally yields lambda cubed minus 9, lambda squared plus 25, lambda minus 24 equals 0. Factoring, for example by testing lambda equals 1, 2, 3, 4, shows that lambda equals 3 is a root, giving lambda minus 3 times lambda squared minus 6 lambda plus 8 equals 0. So the remaining roots are lambda equals 2 and lambda equals 4. Therefore, the eigenvalues are 3, 2, 4. Explanation: some matrix shapes let you read eigenvalues directly without any calculation. Diagonal matrix D equals diag of D1 D2 up to Dn because D minus lambda I equals diag of D1 minus lambda up to Dn minus lambda, and the determinant is the product of D1 minus lambda through Dn minus lambda. The characteristic equation is D1 minus lambda through Dn minus lambda equals 0. Hence, each diagonal entry Di is an eigenvalue. Upper triangular or lower triangular matrix, all entries below or above the main diagonal are 0. The determinant of a minus lambda I is still the product of the diagonal entries ai minus lambda. Therefore, the eigenvalues are simply the diagonal numbers 11 to 22 up to n. An example: U equals matrix with first row 5 2 1 second row 0 3 4 third row 0 0 minus 1 has eigenvalues 5 3 minus 1. Block diagonal matrix A equals matrix with block B top left 0 top right 0 bottom left block C bottom right, where B and C are smaller square matrices. The determinant of a minus lambda I factorizes into determinant of B minus lambda I times determinant of C minus lambda I. Consequently, the eigenvalues of A are the union of eigenvalues of B. And C. This is useful when a large system naturally splits into independent subsystems like a mechanical model with two uncoupled masses. Often the determinant det a minus lambda I contains many common factors that can be removed by simple row or column operations, just like solving a linear system. These operations do not change the determinant up to a known factor, so you can keep track of it. Illustrated example: matrix C equals a 3 by 3 matrix whose rows are 1 2 3 2 4 6 3 6 9. Notice the rows are multiples of the first row. The matrix is rank 1. Step 1. Form C minus lambda I equals 1 minus lambda 2 3 2 4 minus lambda 6 3 6 9 minus lambda. To simplify, subtract 2 over 1 minus lambda times the first row from the second row, and 3 over 1 minus lambda times the first row from the third row, assuming lambda not equal 1. This creates zeros in the first column below the pivot. After these operations, the matrix becomes up to a factor open parenthesis 1 minus lambda close parenthesis squared. 1 minus lambda 2 3 0 open parenthesis 4 minus lambda close parenthesis minus 2 times 2 over 1 minus lambda 6 minus 2 times 3 over 1 minus lambda 0 6 minus 3 times 2 over 1 minus lambda open parenthesis 9 minus lambda close parenthesis minus 3 times 3 over 1 minus lambda. Carrying out the algebra gives a block upper triangular form whose determinant is open parenthesis 1 minus lambda close parenthesis times open bracket open parenthesis 4 minus lambda close parenthesis open parenthesis 9 minus lambda close parenthesis minus 6 times 6 close bracket minus dot dot dot. After simplification, one finds the characteristic polynomial equals negative open parenthesis lambda close parenthesis open parenthesis lambda minus 14 close parenthesis open parenthesis lambda minus 0 close parenthesis. Actually, because rows are linearly dependent, lambda equals 0 is an eigenvalue of multiplicity 2, and lambda equals 14 is the third eigenvalue. The key idea: using row operations turned a messy 3 by 3 determinant into a product of simpler terms, saving time during exams. Explanation: when an eigenvalue repeats, we talk about algebraic multiplicity, the number of times that lambda appears as a root of the characteristic polynomial. This is different from geometric multiplicity, which counts independent eigenvectors, but for calculation we first check algebraic multiplicity. Example: matrix D equals a 3 by 3 matrix with entries: first row 6 2 1, second row 0 6 0, third row 0 0 6. Because D is upper triangular, the characteristic polynomial is 6 minus lambda raised to the third power equals 0. So lambda equals 6 is a root of multiplicity 3. Algebraic multiplicity equals 3. To verify, compute the determinant of D minus lambda I equals 6 minus lambda raised to the third power directly. If you obtain the same lambda from a 2 by 2 or 3 by 3 polynomial more than once, write it as lambda to the k, where k is the multiplicity. In exams, you may be asked to state both the eigenvalue and its multiplicity. For example, lambda equals 6 multiplicity 3. A quick check: after factoring the polynomial, count the exponent of each distinct factor. That exponent is the algebraic multiplicity. Short answer, 2 marks. Find the eigenvalues of the matrix A equals open bracket 0, minus 1 close bracket open bracket 1, 0 close bracket. Solution: a minus lambda I equals open bracket minus lambda, minus 1 close bracket open bracket 1, minus lambda close bracket. Determinant equals lambda squared plus 1 equals 0, therefore lambda equals I minus I. Multiple choice 1 mark. Which of the following is always an eigenvalue of an upper triangular matrix? Option A, sum of diagonal entries. Option B, any off-diagonal entry. Option C, a diagonal entry. Option D, product of diagonal entries. Correct answer: option C, a diagonal entry, because each diagonal entry satisfies the characteristic equation. Full solution, 5 marks. Compute all eigenvalues of the block diagonal matrix M equals open bracket 2, 0, 0, 0 close bracket, open bracket 0, 2, 0, 0 close bracket, open bracket 0, 0, 3, 1 close bracket, open bracket 0, 0, 0, 3 close bracket. The matrix consists of 2 blocks. B equals open bracket 2, 0 close bracket, open bracket 0, 2 close bracket, and C equals open bracket 3, 1 close bracket, open bracket 0, 3 close bracket. Eigenvalues of B are the diagonal entries 2 and 2, with multiplicity 2. C is upper triangular, so its eigenvalues are the diagonal entries 3 and 3. Collecting M has eigenvalues lambda equals 2, multiplicity 2, and lambda equals 3, multiplicity 2. If required, write the characteristic polynomial. Open parenthesis 2 minus lambda close parenthesis squared times open parenthesis 3 minus lambda close parenthesis squared equals 0. These examples illustrate the range of formats you may encounter and how to answer them efficiently.